Okay, good. Okay. Last time we finished our class with the cylindrical coordinate, right? Now we going to the another topic on Dirac Delta Function. Right. Now we going now we are going to see the function that we actually had as a homework. Remember the one that you asked, why it is 0? Remember, we have a vector, right? Vector function like that. V equal to 1 over r square and with the unit vector r. All right. So if we look at this vector, it's like we have a actually we have a vector going outward like this, right? And the further away, the shorter the vector, right? When you go away from the source, the origin, the vector becomes shorter and shorter and shorter and shorter like that. Is that right? I think one of you guys have it on Mathematica, right? Did you?
Yes.
Is it like this? So it's getting smaller, smaller, and go on,
Yes.
What? What did you just say?
I just say yes.
Oh, okay. So it's like that. So it gets shorter, shorter, going further away from the origin, which is here. Now we looking for if you look at the vector field here, you can imagine that its divergence should not be 0, should it? It shouldn't be 0. But our homework tell us otherwise, right? It tells us that the divergence of this function is actually 0 from homework, from our homework. And you guys, like some of you guys had some questions. Why is it 0? I mean, from what we see here, it shouldn't be 0. Actually, it's not 0. Okay. And if we, doing it like just doing it like this straightforwardly, we have 1 over r square, right? D by dr here and r square here and 1 over r square, right? And this one cancel each other out, and we have to take the derivative of 1, which is constant. So we basically get 0. See, this is our homework. So something is not right here. Let me check. We know that this one here, we do the volume integration, right? It's equal to VdA, like that. This from what theorem here? This one is Green theorem, Gauss theorem, and what else? Divergence theorem. There are too many names of it. Okay, but we normally will say these two here. All right, and using Gauss theorem or divergence theorem, we actually can see the solution is quite different here. Okay, let me try to do this integration. First, we have v dot dA here, which equal to the integral of the vector, right? Which is 1 over r square here. Let me put s r prime here, and this is the vector, the unit vector of r dot dA here. Our dA is what? Our dA is basically in the direction of r, right? Which will be this one r square here, sine theta dr d theta d phi. So anyone don't agree with this? Do you agree? This is dA here. In the spherical coordinate is this one. Okay, something d theta d phi. Something is wrong here. Come on, guys, get involved. Something wrong here. Is this dA here? Let's go back to see what is our dA here. It's r square sine theta d theta d phi. That's dA in r direction. So it's r square sine theta d phi d theta d phi, which is correct, right? But when we put it here, something is weird here. This one shouldn't be here, right? Let me put it like that. Do you agree here with this expression? You know, right, why I use R palm here? Because I don't want it to be R. Okay. Or you can put it as R if you want to. I just want it to make it dummy variables. Okay, let me put it this way so you won't be confused. Here, R square here, R square here. Okay, this R square cancel each other out, and R dot R is 1 here. So we have the integration of sine theta d theta d phi. So we have two integrations, so we have to put two integration here. So these two integral sign here, we need the upper and lower limit. What is the upper limit of this? You know it, right? If you consider d theta is 0 to pi. If you consider d phi here, it's 0 to 2 pi. So our solution will be 4 pi. What is 4 pi? But if you look here, it's 0 here. So what's wrong here? This one is always correct. Was it? So something is not right. So we have this thing here. Equal to this. But now we did the calculation and we have this thing is 0 here. This thing is 4 pi. They're not equal. Something must be wrong here. Okay. It's impossible. So this thing, if this thing correct, it means this thing is incorrect. Is it clear? If this thing is correct, this thing is incorrect. But this thing is always correct, as I say to you. This thing is always correct. Okay, so the incorrect thing is must be this one here. Must be this one here. So now what are we going to do is we're going to look into the problem. So what is the problem? The problem here is the origin here. Is the origin is here, where r equal to 0. Let's take a look. Okay, let's consider this again. V equal to 1 over r square r. So at r equal to 0, our v, vector v here, goes to infinity. This is our problem. So it means V is blows up. Blows up means it's just, it's boom. It's a lot. Too much เหมือนกับลูกโป่งแตกประมาณนั้นนะ blows up ระเบิด go off อย่างเงี้ยนะครับก็คือ blows up เหมือนกัน so we have the problem here at the origin. Any questions? Any question here? No? Everyone understand what I just talked about, right? So this actually not just happen in electromagnetic theory. It also happen in gravitational Newtons. No, consider this if we call it gravity, here is G, right? M1, M2 divided by R square. Here. You can see that the same thing happen here. It's the same thing. This thing is constant, so it can consider to be 1 here. If it's like that, it becomes like this. You see, it's just the same thing. So anything with the problem like this, we have R square here. When R equal to 0, the vector, blows up. This is the very normal, actually, behavior in physics. Because at the point R equal to 0, it is where the source is. It is where the source is. For example, if we consider this function, it's like we have an earth here, and this is R0. It's where the source of the gravitation is this earth. This is very important. It is where the source is. Okay. Any question? No. Okay. So this is a weird behavior, but actually it's normal in physics. We can consider it like, it's a weird function. I have it wrong. No, weird or strange. All right, it's really weird, but we're lucky that we have a mathematical objects. We have to cope with this problem. We use an mathematical object called Dirac Delta Function. Okay, we use this. You will see this function, this Dirac Delta Function, in physics a lot. If in particular when you're doing theoretical physics. Okay. This concept is really important, where the divergence of 1 over R square is not 0. This is basically the heart of electrodynamics. That's why I keep talking about it. I don't want you to, I don't want to pass it and you don't understand a thing about it. So normally we use Dirac Delta Function to represent a physical source. Okay. For example, we have an Earth over here, like a planet or something. We can represent the planet with this Dirac Delta function. Normally, we use this as a symbol for Dirac Delta function. It's the representation of a physical source here. This is the source. You may feel that it's how it represents the source. Okay, let me show you. First, we consider one-dimensional Dirac Delta function. Okay, we consider one-dimensional Dirac Delta function. So if I draw, okay, I draw something very simple here. Okay, this is x here, and this point is an A here. When we're talking about Dirac Delta function is like this. It's like you have a peak at A here. So the area, okay, let me draw the area under the curve here. This is Dirac Delta function. Okay. The area of this thing here, under this thing here, is always the area is equal to 1. Okay, which means that the integration from minus infinity to infinity of Dirac Delta function, dx here. Okay. One moment. Sorry, this integration is equal to 1 here. Let's continue here. Any questions? So normally when we're talking about this Dirac Delta function, and I say that it's the representation of a source, it means the source is here. This is our source located at A in space. Okay. If A is equal to 0, it means that our source is right here. All right. And the area under curve is always 1 here. Any questions? Really quiet. Okay. Any questions? Okay. Now, next, we know that the area under curve is always equal to 1. And the other thing is, if you look at the function here, okay, we can say that Dirac delta function of x is equal to 0 if x is not 0. Okay, what does this mean? It means that outside the origin where x, see, this thing mean that the source is located at x equal to 0, which is this one. Yeah, this curve here. All right. So if x is not equal to 0, so it's not this point here, it's the point, away from the source. Away from the source. Everything is 0 here. You might think that, okay, Ajahn, why this thing is 0? Because you can see that there's some value here, right? There's some value here. Normally, when we think about Dirac delta function, the actual function is basically just a straight line like that. It's just a line. It's just really, really thin. Mean that the width here is really, really small, like a needle point. It's like this. So everywhere else is 0 except at the location where the source is. Is that clear? So what happened at the source if x equal to 0? It become infinity because these lines go to infinity. But its area under curve is 1. So this is the basic property. This is the property. Okay, this one is the property of the Dirac delta function. Any questions? Okay, no questions. Everyone understand it. Good. So let me draw another plot here. Let me say here. Okay. Now let me put another Dirac delta function here. So I put it like a line here. Okay, and this thing is a here. Okay, this is our Dirac delta function at x equal to a here. Okay, I only write this down to make it correct. That's all. Because this happened at equal to 0. So when we move the origin of the source to a, your Dirac delta function is like that. But if you're moving away from here in this direction, like this, for example, you have this line. Okay, this maybe b is become Dirac delta function of x plus b. All right, you know it. This is b here, not a. This is where it is at b. Any questions? You can move your source anywhere you want. You can move this here, but your a must be, something else. Let's say you move this. Let's say that you move this line to a. It become like delta function Can you hear me?
Yes.
Yes.
I think my internet just went off. Okay. Let me share the screen again. ผมหายไปนานไหม
ไม่นานมากครับ
ถึงตรงนี้ไหมเข้าใจ fx ตรงนี้ไหมฮะ Do you understand this fx here?
Can you explain again?
Okay. Let me re-explain the whole thing again here. Okay. Before I draw this fx, I just tell you that okay, this Dirac Delta function can move around, right? Can move, you know. When you move this Dirac Delta function, it means that you move your source of, you know, electric field, source of gravitational field, anything. So you can move your source around here. You know, if you move it here, you can say that this thing is 2a here. Your Dirac Delta function become okay. And if you move away here to the other side, it become x plus b. All right. This is what I just told you before it went off, I believe. And now, if we have a normal function, like just general function, you know, coming in. Okay, let's use this color. Let's say I have a normal function coming in like that. It's fx. Okay. And now I want to find the product. The product of fx and Dirac Delta function x minus a. You know, a can be 0, can be anything, depend on where your source is. Okay. A can be anything. Okay. Can be anything depending on where your source is. All right. So when I say it's a, it means that your source is at a, x equal to a. That is where your source is, which means it's here. It can be a point source. Normally, it represents a point source without any dimension. You know, no physical size. Okay, it's a point source. All right. So what happens when we multiply it like that? When we want to find the product of it. Okay, so we just look at the figure here. So this is our fx. This is our Dirac Delta function. When you want to multiply it, as this here tell us, if x is not equal to 0, it's 0 everywhere. So this definition, you can say that if I put like that, if I write down it like that, x minus a here, it means that it's 0 if x is not a, and it's infinity if x is equal to a. You understand, right? It's quite clear here. So from this definition, we know that away from a here and away from a this way, this direction, is 0 everywhere. Meaning that if you multiply this function to Dirac Delta function away from a, it becomes 0. So it only has a value at this point. What is this point here? This point is equal. Yes, is f equal f of what? F of a, right? This thing is fx here, and this thing is x equal to a here. So at this point is x equal to a. So this one is basically fa of Dirac delta function x minus a here, and anywhere else is 0, right? Anywhere else other than a here is 0, so there's no need to write down. Is it clear? So from what I am trying to explain, you can write it down as a mathematical expression like this. Any questions? No? A can be, as I say, no? As I say, it can be anything. It depends on where your source located. Okay, now let's continue our quest with the Dirac delta function. So from what I just wrote down, let me write it down again. Okay, if x minus a here is equal to f0 x minus a. Okay, no, not f, not x0. It must be a. Okay. Any questions? Now, I want to do the integration of this function from minus infinity to plus infinity. Let me write down. Okay, minus infinity to plus infinity of fx. Dirac delta function x minus a here equal to fa here. Dirac delta function minus a here. So the problem here is I forgot to put this. Okay. All right. If you look here, f at a, this one is basically constant. So I pull it out of the integral. So I have this. So what is this? Give you. If you understand what I said previously, prior to this topic, you must know that what is the value of this integration? What is the result of this integration?
1.
1, yes, it's equal to 1. It's equal to 1. So we actually having the final expression here. Of f function of a here. Okay. If a is 0, it's like that. Okay. Any questions? No. No questions. It's clear to you? Okay. No one answer. Okay, let's try an example here. Our example is simple. It's just from 0 to 3. It's just from the book. Okay. This x to the third multiplied by the Dirac delta function at x equal to 2 dx. What is the integration? Okay, let me draw this picture here first. Okay, this is the x here, and this thing is y in here. Okay, oh, where is the Dirac delta function x equal to 2 is here. Okay. Any question? Is that clear? Now, what is x to the third? This one is fx here, and this thing is right. And what is our fx? Let me use the orange. Our fx is like that. Like that. Okay. But if you go into the other direction, it's like that. Okay, it's like that. But we only consider the positive side in quadrant 1, in the first quadrant. So this thing is x to the third. So the result, what is the integration from 0 to 3 here? So it's cover. You can see that our integration cover this range and cover the Dirac Delta function. So we don't have problem. It's really simple, right? Our solution is what? It's this one. It's equal to x. No, it's equal to, sorry, it's equal to 2 to the third, which is what? Which is 8. Really simple. Okay. Now. How about if I change the integration from 0 to 1, x to the third, Dirac Delta function, x minus 2. Can you tell me what it is? What it is? What is the result of this? Come on, guys. Say something.
I think it's 0.
Okay, now you can raise your hand. Who think it's 0? Let me check who raised your hand. You can raise your hand. Who think it's 0? Who think it's still 8? 2 to the third? No one raised your hand. Okay, Silvit think now. Who raised your hand? It means the result of this integration is 0. Only Silvit raised your hand. The rest is not 0. No. Chanta Nipa. What do you think? Okay, Chanta Nipa is not here. Chutima, do you think it's 0? Or do you think it's 2 to the third?
I'm not sure how to calculate this one.
Okay. Let me go back to our work here. Okay, our integration is going from where? From 0 to 1, which is somewhere here. So our limit of integration confine us only in this region. All right. And our Dirac Delta function is not here. So it's 0 other than 2, right? It's 0 everywhere, this way and this way. So any function that multiply to this Dirac Delta function is 0 here. There's nothing here. It just flat line here. Okay. If you, let's say, if you, I do the integration from 3 to 5, it means 3 to 5 here, right? So I do the integration from this to this. It's not at 2. So it's 0 everywhere else. So it's 0 here. So you use the function multiply by 0. So it's always 0 here. Okay, it's 0. So if I draw a curve for this integration, this thing is 2 here, and our function that's previously like that, like this, right? This our function. When it's multiplied by the Dirac Delta function, this thing is fx here. This thing is Dirac Delta function x minus 2 here. When this yellow dotted line multiplied by the Dirac Delta function over here, it's no problem. This thing is if fx equal to 2, right? Which is this one, which is 8, right? Okay, but everywhere else it's like that. Okay, this is the result. It's 0. It's flat line 0. Okay, there's nothing else. The Dirac Delta function doesn't have any value outside 2. Okay. So what the calculation you do? You don't have to do anything. You look at the figure. You can see that okay, it's not covered the Dirac Delta function. It's 0. So when you consider the Dirac Delta function, you have to really be very careful. Okay, careful about what? About your limit of integration. If it's outside the Dirac Delta function, it's 0. You don't have to consider. Don't have to calculate anything. But if it covers the Dirac Delta function, your function is equal to that location. You know, your function at that location. For example, f of 2. You know, as in this example. Any questions? Is it clear?
Yes, teacher.
Yes. Okay, good. So now we know that if Dirac Delta function is a function, all right, what happens if we multiply a constant? Okay, let's consider another example. Okay, this example is we want to show that this Dirac Delta function of xk, k is a constant multiplied by x is equal to 1 absolute k here of Dirac Delta function x here. We want to show that this is true where k is any constant, okay, but not 0. Okay, we want to show this. Okay, now we still have some space left. Okay, to do this, first we have to consider the integration of this Dirac Delta function. Let's consider this from minus infinity to infinity. If you do the minus infinity to infinity integration, it's of course cover our Dirac Delta function, because our Dirac Delta function must be somewhere in the space. So when you integrate, when you do the integration from minus infinity to infinity, it always cover the Dirac Delta function. Okay. Okay. Let me of fx. This is our test function. We multiply to the Dirac Delta function, and we do this. Okay. Now, because there's a multiplication, the product of k and x inside, let me do the normal, like, you know, when we do the integration, we always, okay, let's change the variable. Let's set u is equal to kx here. Okay. And x is equal to u divided by k, and du equal to k dx. All right. Any questions? So over dx from here, we have our dx is equal to du by k. All right. Anytime, every time you actually change the integration variables, you have to reconsider your limit of integration. Okay. Okay. So our x is from minus infinity to infinity, right? Our x we indicate with respect to x. So this thing is x here. This thing is x here. Now, if we put it back here, x is minus infinity. So multiply by k is become minus infinity. So if x is equal to infinity, u is always also infinity. So the limit of integration is still the same. All right. It's still the same. But the problem here happens because our k is just any constant, just not equal to 0. It works. So it's also include minus k, okay, and plus k. So it can be negative or positive, just not 0. It can be anything else. Okay, but since I just told you that if x equal to minus infinity, u also minus infinity, right? And if x is infinity, u is also infinity. But if k is negative, the sign change, right? If k is negative, is it minus something? It's become positive, this thing become minus. So this thing is a little bit awkward here. So we want to confine our calculation. Let me put the absolute so that we don't have to worry about the sign. Okay. So before we do that, let's continue our calculation. Okay, if fx here and dkx here, dx equal to what? Plus and minus, right? Depend on the sign of k. Okay. So our indication from minus infinity to infinity, f u by k here, because it's fx. So just we put x here into that calculation. And what else? And our Dirac delta function become Dirac delta function of u, right? And du by k. So this is our integration. Okay. Any questions? I didn't do anything difficult. I just make it simple. So the product of this is become this one, the integration. Any questions here? No? Okay. So in this case, is our Dirac delta function is u. So where u in the function where u is 0, right? So this thing is become equal to plus and minus integration. I don't need the integration anymore. I just do the integration. Okay, this thing is become f where u is, this thing is actually Dirac delta function of u minus 0 here. So where u is, put 0 here, so it becomes f0. Okay, f0. And this thing is divided by k here. And then we can write it down like that. Okay, so let's check this. This lower sign here, the plus and minus here, this function, okay, use the minus sign when k is negative, okay, negative, and plus when it's otherwise, okay. Any questions? So by using this relation, we have this actually. Okay. Okay, if this the same here, if so this thing is actually proved to be correct. And now we can write down the integration in the other form. Say, okay, let me write down from minus infinity to infinity fx is equal to multiplied by kx dx here must equal to minus infinity to infinity f of x here. Since this thing is equal to 1 over k Dirac delta function x, so we just put it here 1 over k Dirac delta function x here. One over absolute k here. Okay, it's equal. No questions. Anything want to ask? Okay, if no one is asking anything, okay, here's the homework. Okay, our homework is problem number 1.44 and 1.45 and 1.46. Any questions? So this is our homework. Don't forget to submit your homework on e-learning. Okay. We just study the Dirac delta function in one dimension. What happens if we are doing it in three-dimensional, which is the typical space for us? We live in three-dimensional space. Okay, so three-dimensional is more real and practical. So we want to study the 3D Dirac delta function. Okay, the 3D Dirac delta function here. Instead of having just x, 3D Dirac delta function is like that. Okay, we have to put number 3 here, and in Cartesian coordinate is like that. Okay, this is in Cartesian coordinate where x, our r is xi here plus yj here plus zk here. Okay. Any questions? No. And again, we have to consider its characteristic, right? So we have to integration from all space instead of writing down the three integration. Well, this thing is like, okay, in all x, y, z. In all space, okay, and equal to what? Equal to this minus infinity, 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 and what? Dx Dirac delta function of x, Dirac delta function of y, Dirac delta function of c, dv. Okay, and what is dv here? dv is just dx, dy, dc. What do anyone want to guess how much would that be? The whole integration give you what? What is the result? What is the consequence of this integration? Can you tell me what is the result here?
I guess it's 1.
Yes, it's 1. Because there's no function here to worry about. So it's become it's 1 here. So it's just 1. Now, if we want to generalize this function, we can say that over integration or space f of r here. Okay, right. Let me write down in general form here. Okay, is equal to what? Can you tell me what is in here? It's a. Okay. Okay, I forgot the integration again. Any questions? No? Okay, it's clear, right? Now, we go back to the original problem. What is our original problem? Our original problem is this thing, right? V is equal to 1 over r square, like that. Okay, and we use the divergence theorem and prove that it becomes 0 equal to 4 pi, right? And this thing is from the integration by surface integration. This thing is volume integration, like that, right? This thing is divergence theorem, but this thing is 0, this thing is 4 pi. So this thing is basically not correct. To have it correct, right? To make it correct, this integration here must equal to this. Right? Do you believe me this? So this is the correct one. It must be equal to this term here. Otherwise, it's not 4 pi, right? Why is it 4 pi here? Because over this integration is basically equal to 4 pi, right? Over integration or space. And Dirac delta function, 3-dimensional dv here. And this thing, the integration of this, the whole thing is 1. So it become like over this integration here, the divergence here is equal to 4 pi. And if you look here, 4 pi and this is 4 pi. So they now equal. Good. Is that clear? So from this point, we know that divergence of 1 over r square r here equal to 4 pi Dirac delta function, like that. All right. Any questions? No? Always quiet. Is that clear? No, but everyone understand everything. That is really neat.
Teacher,
Yes.
how do you know that the integrate of divergent v dv is equal to integrate 4 pi Dirac delta function r dv?
Okay. In order to get this same result as because we believe we actually know that this thing is always correct. So
Okay.
this thing give you 4 pi. So this thing must also give you 4 pi. So in order to give you 4 pi, sorry. In order to give you 4 pi, the whole thing here must be 4 pi. Is that clear?
Do we
So
need to,
we must believe that the divergence theorem is correct first.
yes.
Mhm.
But why do we need to put the Dirac delta function in that integrate?
Because we need to do the integration of the whole
Oh.
volume, right?
Because it's short or something.
Sorry?
Because it had the short at that point or something. Or it just you said that we want to integrate at all boundary.
What is your question here? Your question is why this thing is equal to this?
Yes, I know that we use the divergence, but why do we need to put the Dirac delta function in that? Because it has Dirac delta function, so we need to put it here because it is at the source, right?
Yeah, there's a source in there. And if you don't put the Dirac delta function in there, right? You say that this thing is equal to 4 pi alone. You have to do the integration dx, dy, dc. And you will get infinity. Right? You get 0 also, not infinity. So to make it equal to 4 pi here, you have to put the Dirac delta function because we know that the Dirac delta function is integration always 1. From minus infinity to infinity is always 1. Always equal to 1. Okay, this thing I write down here. So we can just say that this thing is equal to 4 pi. It's not like that. You have to do the integration because from this point of view here, you do the integration for the whole thing, you get 4 pi. So you have to do the volume integration to get 4 pi also. To do that, you need to integrate dv. And to make the dv equal to 1, you have to integrate it with the Dirac delta function. Otherwise, it's not 1. Right? See here, it's equal to 1. All right. Yeah, no questions? Okay. So it doesn't mean that we have to use only R here. We can write down the general form of it like that. Okay, divergence of any function here. It can be anything, right? Equal to 4 pi. Okay, we use this a lot also. Okay. And you can say that if consider our work here, this, if you remember, what is this R here? is the separation vector จำได้ไหมremember separation vector recall that all right this r is equal to minus r prime right can use that also any questions so this is okay really important relation no question at all all right okay do we have any space left somewhere here okay let me move to another page it's really tight already okay let me put another page here okay let's continue here okay from what we know here we know that the gradient of 1 over r gradient of 1 over r you know if you try it at home you will get this r square similarly if the gradient of 1 over r here also equal to r square like that okay it's the same thing here okay so we can put this value into this okay and you can see this thing the same thing here we can put that is that clear I didn't do anything right I just substituted and this thing is equal to this thing is equal to minus it's become Laplacian of 1 over r here okay and this thing is equal to what 4 pi this thing is equal to 4 pi okay just put it in so we have this any questions no no questions okay if there's no question let me use the example here okay let's consider an example let's evaluate this integral j is equal to integration volume integration r square here plus 2 and divergence of r divided by r square dv okay and this thing is actually very simple here we know that this thing is equal to what equal to 4 pi Dirac delta function of 3-dimensional is equal to r here right and so our integration is really simple here and 4 pi
Teacher,
and
can,
4
can
yes.
you move the slide above a little bit?
okay
Thank you.
and this thing we had pull 4 pi out of the integration and we just do the r square plus 2 here okay from this Dirac delta function, we know that our source is at the origin, right? Because this thing is minus 0, right? This thing is equal to r minus 0. So our source is at the origin. So we can, the result of this integration is f0, right? So our f is this one here, and actually it's a function of r here. So we can substitute r with 0 is 0 squared plus 2, right? So we have 2 here. So our integration becomes 4 pi and multiplied by 2, which is equal to 8 pi here. So our j is equal to 8 pi. It's very simple. All right. Or you can, if you want, you can try to do like, like normal, try to do all the integration. You can change. The other way you can do is you just convert this into surface integral. Okay, you can try that. But using that integration is a lot easier. Use Dirac delta function is a lot easier. All right, we don't have to, do the normal. If you want to see the way you do it, like, with basic concept, the divergent concept and anything else, you go back to look in the book. There are the solution number 2 for this problem. Okay, but I'm not going to go through it. It's a waste of time here. So let me give you, this thing is much more fun to give you here. It's giving you homework is my favorite here. Okay, 1.48 here and 1.49. Okay. Any questions? Okay, and you have reading homework. Okay, your reading homework will cover the last part of this chapter, which is the topic number 1.6 in the book. Go and try to understand what you are reading. Okay, you read this topic here. This topic is quite important actually. One thing that is very important is this one here. Curl of any vector if it is equal to 0. This function, this vector field here, f here, can be written as a gradient of any potential, any scalar function. This thing is scalar function. Okay, if curl of vector field is equal to 0, that vector field can be written as the gradient of any scalar potential. All right. But if it's not 0, this thing is not right. Okay. If it is not 0. Okay. No question. And just to keep our space really concise, I give you homework. This is the final homework of this chapter. Okay. The problem 1.54. 1.57. Try to keep up with the homework. Don't just, leave it and do it in the last minute. You will not have time to do it. And 1.59. 1.63. And 1.64. Okay. This is your final homework for this chapter. Any questions? Now we're going to study another. And actually, I want to finish this in the last page, but it's impossible to fit this into really small space in there. Okay, now we're going to the chapter number 2 here. It's called electrostatic. Now, in this chapter, we will study electric field and Coulomb force and its relation to the field here. So we will begin with very simple thing here. It's called Coulomb's law. Coulomb. We know that Coulomb law is equal to F 1/4 pi epsilon naught Q divided by R square and R here, and we need to have another Q here. Okay, this thing is Coulomb law. Okay, and what is our epsilon naught? Our epsilon naught is the permittivity. Permittivity of free space, and it's equal to 8.85 times 10 to the minus 12 Coulomb square divided by Newton meter square. Okay, and F is Newton, is the Coulomb force. Any questions? No. And what is R here? R is R minus R palm. Okay. Okay, before I go further, so when we talking about electrostatic, it's very important to know that the word static means that there's nothing change with time. Okay. There's nothing change with time. Okay. So it's quite static. It's constant over time. It doesn't change. That means static. So it means electric field or anything doesn't change with time. There's no time dependent. Okay. No time dependence. No time dependence. Okay. This is really important. Any questions? No? Okay. So let me draw figures for you. To understand this, you must see the figure here. Okay. You can write down like 3-dimensional. Let's say you have a Coulomb, a point source here. You know, it can be Q here and it can be Q here. All right. So you have two vectors. All right. If we say that this thing is R here, palm, this thing is R here. Okay. When you use R palm actually representing the location of the source. Okay, the source, location of the source. Okay, and here representing the location of interest. Okay, we interest that what is the field here, the force here. Okay, so now we have another coming in. What is this vector here? This vector is here, right? It's the separation vector. We talk about this, and this separation vector is equal to minus half. Okay. Okay. It can be three-dimensional. So this is the Coulomb force. Now you can read it Coulomb or Coulomb. Normally, it's the French name, so people can read it Coulomb. You don't have to pronounce M and B here. You can call Coulomb force. Now let's continue to this thing is the Coulomb force. Okay, you have the force. Now to see it further, we study the what called is the electric field here. Actually, we talked about this before, right? When we start the class in the first time, I think I actually talk about the vector field and the electric field or gravitational field. If you remember, I said that if you have a mass, let's say we have an Earth without any planet around, okay, no other planets, and no human, no life on Earth, only an Earth, solid rock, Earth. This Earth actually produce what is called a gravitational field, but no one actually feel the existence of that field. No one actually see the existence of that field. Okay, but when you add a mass in that field, okay, now that mass that you just added will feel the gravitational pull from the Earth, right? It will feel the force, the gravitational force from the Earth. So when we're talking about the gravitational field, you don't need any mass. You just only have the one mass, the Earth. Similarly, for the electric field, or what actually related to the Coulomb force is the electric field, right? Okay, you have a gravitational field related to the gravitational force. Okay, now we have the electric field that related to the Coulomb force. Can you see the analogy here? So electric field actually relate to the Coulomb force. Okay, just like the gravitational field. Related to the gravitational. Basically mg, right? What is the gravitational field here? It's G. So when we add an M, you get the force, right? Similarly, for the electric field here, it's related to the Coulomb force. It means that if you have a charge here, if you look at this equation here, when you have a charge, like let's say you have Q here, and this Q actually generates electric field here, but no one actually feel the existence of this electric field. To be able to feel or see the effect of this electric field, you need to add another charge into that space. Otherwise, you won't see that in that space there is an electric field in it. Okay, you need a test charge here. You need to have another charge to be able to feel. If you don't have a charge, you won't. It seems like there's no field in that space. Can you see the concept of electric field here? Okay, so because it related to the Coulomb force, we can say that, okay, when you have many Qs, when you have, okay, let me, for a number of charge, let's say you have Q1, Q2, Q3, Q4, and too many Qs here until Qn. Okay, so we have the separation value vector R1, R2, R3, R4 until Rn here. Okay. Okay, a number of point charge. Okay, let me say it's point charge. Okay, this point charge is actually at a distance R away from Q, from a charge Q here. So our force here is this one here, is F1 here plus F2 plus F3. Okay, continue until plus Fn. Okay, until Fn here. Okay, now we write down like that. Okay, 1/4 pi epsilon naught. So everything share this factor. So we pull it out of the equation of the expression. And what is inside here is that Q1, Q, right, divided by R1 square. And it's R1 here, plus 1/4 pi epsilon naught here, Q2, Q divided by R2 square here, and plus 1/4 pi epsilon naught here, Q3, Q divided by R3 square, plus 1/4 pi epsilon naught, Q4, Q divided by R4 square, and plus continue until Rn or Qn. Okay, since they share the same factor here, actually I just said it, this share factor, we can pull it out of the equation. Our F become 1/4 pi epsilon naught, and we can put this like Q1, Q divided by R1 square, R1 plus Q2, Q divided by R2 square, R2 here, and plus Qn, Q n divided by Rn square here. If you look at it, okay, not just this factor, actually everything has Q in common here. We can pull Q out of the equation. Okay, sorry. Okay, we can pull n out of the equation. We have this 1/4 pi epsilon naught here, and Q out. Okay, we have Q1, R1 square, R1. Okay. Any question? Okay. Any questions here? This is force here. And if you see here, over here, this thing is called the E field. Electric field here. So we can say that our F is equal to Q E. Okay. It's covered this also. The whole thing is E field. So what is this force tell you? It's the force that act on Q by what? By Q1, Q2, and Qn. Okay. If I draw a graph for this, for space here. Okay, let me draw like 3-dimensional. Okay. It means you have a chart Q here, and you have this Q actually generate an electric field also. But okay, let me write down. Let's say first we have Q1 here, and Q2 here, and Q3 here, and Q4 here, and we have too many Q here, allow a lot. And all this Q here actually generate an electric field without seeing, without us seeing it. And to be able to feel the force, we put a charge Q here. It can be positive or negative. It depends on us. So when we put this Q in here, and this Q will feel the force from here. This thing is R4 here. And let's say this thing is Q5, and you will feel this Q5 here. Okay, this thing is R5. And you can feel this R2 here. You can feel R3 here. You can feel R1 here. So this Q will feel all the electric field from point charge Q1, Q2, Q3, Q4. All right. So we can write down the force is the summation of the field from each charge multiplied by Q. All right. So from here, E can be written as a 1/4 pi epsilon naught here, and I here, and Qn here, Qi divided by Ri square Ri. Okay, this thing is E field. Okay, I can be from 1 to n. This is for point charge. It's the electric field of point charge. The electric field of short charge. Okay, so all this small q here is our sources. Okay, any questions? No. Okay, if I want to draw a vector, a proper vector here, let me subtract this. I want to draw a proper vector for all q here. Let's say we have, let's say I will draw like q1 here, and q2 here, and maybe q3 here. Okay, and we want to find the electric field over here. This is where we want to find the electric field here. Okay, let me move it a little bit down here. It is P here. Okay, this vector, and this vector here and this vector here. Okay. Okay. This is palm tree. This thing is palm. Oh no, it's not like that. Okay. Palm 3, palm 2, palm 1. Okay. This is the vector, the source vector. Remember we talked about this. And from, let me use the green color here. From point here until here. What is this vector? Can you tell me? This vector is the point of interest. Remember, we want to know what is this field inside here. What is E here? E equal to what here? And let me write down. Okay. And what is this vector here? And what is this vector here? And what is this vector here? Okay, let me move this Q here just up a little bit so it will not.
Acha ครับเสียงอาจารย์หาย
Okay, let me move this just above, on top here a little bit so it will be easier to draw the vector here, the separation vector. Okay, this one is another vector here. Okay. So the gray line is the separation vector. This thing is here, 1 here. This thing is 2 here. This thing is 3. Okay. So to find the electric field here, E here is will be equal to 1 over 4 pi epsilon naught Q1 divided by R1 here plus Q2 divided by R2 square, R2 here, plus Q3 divided by R3 square, R3. Okay, from this figure, we can find E field really easily because it's all point source. Any questions? So this is a discrete source. So it's like a point. There's no physical dimensions to it. Okay. Let me give you an example. Actually, this example is really simple. You see it when you study physics 1. Let's say we have a point. Let me draw a line first. Okay. We draw a line here and say that we have a point Q here and point Q here, and we want to find in the middle. Let's say we want to know that what is the field here. What is the field here at this point? All right, we want to know what is the field here, and this is the height, like C. So this is in X direction, this thing is in C direction. And you can say that this thing can be H here. Okay. And the distance here is D divided by 2 here, D divided by 2 here. So the total distance over here is D. So we want to find E field at P. What do we do here? Okay, since E is a vector, we have to be very careful. Okay, let me draw a line here. So actually Q here actually moving this way here.
อาจารย์ครับจอมันหยุดแชร์ไปแล้วครับ
อ้าวอะไรวะ
เพิ่งหยุดตะกี้
This is really strange. It's keep. Okay, can you see it now?
no
Okay.
See? Can you see it?
No.
No. Okay. Something is wrong with the internet, maybe. Let me share it again. Yeah. Okay, can you see it?
Yes.
Okay. I just explained this. So we have a point charge Q here, and they are positive. Okay, and we want to find the field here at point P over here, and the separation between these two Q here is D, and we want to find the P, the electric field at point P, where P is in the middle of these two charge. Okay, and the height here is H here. What can we do here? We just do the simple thing here. We just sum them, right? Before we sum them, let's look at this point first. This Q here is the direction here. Okay, the electric field that's coming from this point charge here is going this way. Going this way. This thing is E field here. Okay, let's say this one is, and this one here also the same thing here. Okay, sorry. All right, this thing is E field from the two charges. And if you look really carefully, you can simplify the problem. First thing is that if you see that E field is a vector, so there's a vector E field here, EX here, and there's another E field here, EX here. If I ask you, are these EX equal to each other? Are they equal? These two EX here? Are they the same? They have the same, they are the same, but different direction. Okay, one is pointing this way, the other one pointing the other direction. So we don't have the E field in this direction because they all cancel each other out. All right, we have only one direction here, is this direction. Okay, in this direction, this is our E field. There's only one this direction. Now we know that our solution must have only one component in Z direction. Okay, and it's also help us that we don't have to consider this thing here. We know that they'll cancel each other out. We don't have to worry about it. So we only have to do one side, and you multiply this one side by 2. So you have it already. Okay. Now, let's consider only one side here. Let me consider only this side. And I will multiply 2 later. Okay. This thing is angle theta. Okay. When this thing is theta, this thing also theta. Okay. So our E field here, just from point Q here. Okay. It's equal to 1/4 pi epsilon naught, right? Q divided by R, right? Square. Here. And we know that it's only on C direction. Okay, this thing is over R here. It's the separation vector, right? This thing is over R here. And we know that this thing is the height here is H. So over R is what? So this we have a Pythagoras. We have the normal triangular. Okay, so our R is very simple here. Our R is equal to H square plus D over 2 square. All right. Okay. And we don't have to worry about this thing here. We just, project it onto the C axis ก็คือเราดูเงาของมันที่ทอดลงบนแกน Z เพราะฉะนั้น therefore we have this 4 pi epsilon naught Q divided by R square and cosine theta C. Okay, cosine theta C. This thing is Z direction. And if we want it, we can multiply it by what? By 2, right? But we can, we don't want to have it in cosine. We know that our cosine is what? Our cosine theta is equal to, right? Here we have a triangular like that. So what is our cosine here? Our cosine is what? Is H divided by R, right? Our cosine. So we can substitute this into this. And it's become H over R, right? And what do we have here? We have 1 over 4 pi epsilon naught QH divided by to the third here. Okay, what is R to the third here? R is equal to H square plus D over 2 square. The whole thing is to the 1 over 2. Okay, so when you multiply here, it's become 3 here. So we have E field here, 1 over 4 pi epsilon naught QH in C direction. H square plus D divided by 2 square. The whole thing is to the 1, 3 to the second, to the third, 3 to the second here. Okay, any questions? I didn't do anything. Just simple mathematics. And this thing is only E field from this chart here. But this chart also the same amount of charge. So we just multiply by 2. For the E total here, E total is equal to 2E, right? Because from here and from here they are equal. So just multiply by 2. So we have 1 over 2 pi epsilon naught here, QH divided by H square plus D over 2 square. The whole thing 3 to the second here. Let's see here. Any problem here? So this is E total for this problem. Any questions? It's really simple, right? No question? Is it too fast? Because it's really simple, that's why I go quite fast. And you actually learn about this when you study physics 2 or physics 2, I think, right? You have to tell me where in the lecture you don't understand, okay? Otherwise, you will not be able to do the midterm exam and final exam. I don't want you to fail this class, okay? Try to go back and study and do the homework by yourself. Okay, now I will show you how to check the result, whether it's correct or it's incorrect. Okay, whether it's correct or incorrect. Let me think. Let me tell you what happened if this H here is a lot more than D. So when this H is a lot more than D here, it means you are very far away. These two charges here is really close to each other. See, this thing is H here, this thing is D. Okay, when you go very far away, this two is very small. Okay, it's like you have these two become the same charge here when you go far enough. When H is far enough, D seem like go to 0. So the two charge become one charge. Okay. What does that mean? That means that it means the whole thing become single charge, and your Q become 2 here, and Q become 2Q here. Okay. E field here become 1 over 4 pi epsilon naught 2Q divided by H square. Okay, D is so small that compared to H, it doesn't affect anything. Okay, so you have this. Okay, this thing just behave like a point charge with Q is equal to 2Q. Like you have Q here, you have a point charge here, and you have Q here, and you go very far away and see here. No, this thing is become H here, and you want to know what's the field here, the same thing, and Q just 2Q here. Okay, when you go far enough, the two charge become one charge, but you have to multiply it with 2 because there are two charge and combine together 2Q. From one of them is Q, the other one is Q. So when you combine them, it's become 2Q, but it just behave like a point charge. Okay. Any questions? Try to go back and take a look at the video, okay, and tell me if you don't understand anything, and try to do the homework by yourself. Okay, if you don't do the homework by yourself, you will not pass this course. I'm quite certain. Okay, if you cannot do the homework at all, you may reconsider to withdraw it. I tell you that this course is really, well, it's not difficult if you try, but it's difficult if you don't do anything. You just copy your friend's homework. Okay, try to do it yourself, so you will know that where you don't understand, and you can ask the direct question. Okay, proper questions, to improve your understanding. Any questions? No, I don't want to, pamper a lot. Okay, I'll call it a day today. I'll see you on Monday. No question. Everyone just listen and really quiet. No question. Okay, let's call it a day. Okay. Have a good day, everyone.
Thank you, teacher.
Okay.
Thank you.